this exponential question, you can get pretty far without ever writing down the function itself for a. So I'm going to go for it like that, and then later on I will talk about how we could set up a function. Now, when something is decaying exponentially, or in fact increasing exponentially, it means that every time t goes up by a certain amount, that we are multiplying by something. For example, we might be doubling every 10 minutes or whatever. So we can work out what is happening every 10 seconds by doing 750 divided by 1250. And actually, we're timesing by 0.6, and this is going to be a repeated thing that happens throughout. Every 10 seconds, we're going to times by 0.6. So we can get to 50 and see what's happening by continually timesing by 0.6. So I'm going to do 750 times 0.6. And that gives 450. So actually, that is what is happening after 20 seconds. So that's going to be one of the missing values. And then we can keep going. So next one, if I times again by 0.6, then I'm going to get after 30 seconds, it's going to be 270. And after 40 seconds, 162. Which takes us to 50 seconds, 97.2. So these two are the missing values that are being referenced. Now I'm going to show another way to do it. And this is actually how I did it. I jumped straight into it. So it's just to use the idea actually that is in part B. So they write down the mass as 160 e to the minus 0.055t. So this is method 2. What we can do for A is write down that MA is going to be some initial mass. I'm going to call it M0 multiplied by e to the minus kt. I know it's going to be a decay, that's why I put the minus there. And I just need to find out this constant. It's very similar to this sort of setup. I've got some starting value, and I can actually write that one straight down, and I've got some sort of decay happening. So M0 is when t is 0. It's going to actually be 1250. That means I've got MA is 1250 e to the minus kt. Just need to find out k now, so I can just use any of the other, actually, I say any of the other values, I only have one other value, so I'm going to use when MA is 750. And that will equal 1250 e to the minus, substitute 10 in, minus 10k. Divide through, that's actually going to give me my 0.6 again. So this 0.6 is e to the minus 10k. And therefore minus 10k is going to be ln 0.6. And from this I can work out k. Divide through by minus 10. So 0.05108. And therefore, MA will be 1250 times E to the minus 0.05108t. And from that, we could substitute, for example, t equals 50 in, and I'll just show you what happens when we do that. I'm actually using the exact answer here. So the exact answer times 50. We again get 97.2, and you could solve it equal to 450 and find the value of t. And that would also give you the 20 that's missing there. So it's a longer method, especially when this is 2 marks. I'd say this is a good way to go, but it's also important to understand this as well. So on to part B, we've got another substance decaying exponentially, and here is the model. So determine the value of t for which the mass is half of its original mass. Actually, this is using some of the similar ideas to what I used here, but like I said, you didn't have to do this along the bottom. So the initial mass is going to be 160, and therefore I want to solve AT equals 160 e to the minus 0.055 t. Divide through by 160, it's going to become 0.5. We can solve this in a very similar way. We can take logs and then divide through by minus 0.055. So t is going to be ln of 0.5 over this. Which gives 12.60. So just write it as 12.6. Three significant figures, 12.6 minutes. Then determine the rate of decay of substance B when T is 15. So that means we're going to need to differentiate. It's going to be dmB by dt. And I'm going to multiply. So when I differentiate, the 160 just kind of carries on through. And then when I differentiate e to the minus 0.055, using the chain rule, we're just going to times by minus 0.055. And then the e stays as it is. So yeah, when you differentiate e to the kt, you get k e to the kt. And when t is equal to 15, we can get the derivative at that point, which is, well, it's nearly the rate of decay. It's got to be careful here because the rate of decay is actually going to be, we're going to get a negative here for the rate of change, but the rate of decay is going to be positive, just remembered. So minus 3.856. Therefore, the rate of decay, it's a bit like when you get asked for the deceleration. If the acceleration is negative, the deceleration becomes positive. It's going to be 3.86 grams per minute. Finally, part C. I've got to be honest, this is a baffling question because for only 1 mark we have to compare the decay of A and B. Now the thing is, if you used the method I showed you in part A, you just got this, it's very difficult to compare the decay rate because, we need to compare the instantaneous decay rate, really. I suppose you could look at the decay rate as you could like maybe find the straight line average decay between 0 and 10 and do the same for substance B. So maybe that's the way around it. Otherwise, you're going to have to work out the MA like I showed as the alternative method here, which is quite involved, to be honest. So let's imagine you go this route. This is actually how I dealt with it. Then what we can do, or what we have to then do, is find out dMA by dt over here. And that's going to mean we multiply, very similar to what we did for A, multiply or differentiate 1250 times minus 0.05108 e to the minus 0.0. it's quite tricky to compare these two functions, just like as they are. And remember, it's only 1 mark, so probably a good shout is to just compare when t is minus 15. Sorry, not minus 15, it's 15. When t is 15, okay, and see what we get. Minus 29.67. So we can see that A is decaying at much faster rates at after 15 seconds. Maybe I should just say that this is less than minus 3.856. Okay, you don't need to do any more than that for 1 mark. Just to talk about it in a little bit more detail though, because I thought about it in a bit more depth. I started comparing the exponential aspect because this e to the minus 0.05108, well the minus 0.05108 is less than the, well sorry, it's not no sorry, it's greater than this here, which kind of implies that b, the multiplier, is going to be less, and in fact that is the case. It's just that we start with a much larger amount with a. That's why the decay rate is so much more, because you are, although the percentage decrease is less, the actual amount is more. So this gives rise to quite an interesting conclusion, because you could instead, and I'm going to bring up the mark scheme now, you could instead justify that B is decaying faster. So method one is what I just showed. Um, you need to look at the decay, not just the mass. But the alternative, which you will get marks for as long as you give supporting evidence, is that B is decaying faster, because even though the decay rate itself is not as big, the actual percentage change is bigger. So after 10 minutes, B's mass is 58% of the initial mass, whereas A is 60%. And you know what? That's a way around having to find the exponential function, because you can just take this here and show that we get 60% of the initial mass without having to deal with this formula. Whereas we can put it into what we did from B part. Sorry, yeah, no, we can put it into this formula here, work out the mass after 10 minutes and show in fact it is 58%. So in that sense, the percentage is decreasing faster. So yeah, a bit baffling, especially for 1 mark, but these are two options, and I think if I was doing this question again, I think that's how I would do it. I would do part A using this method in blue, and then I'd do B as shown, and then part C, compare the percentage of the mass left after 10 minutes, avoiding finding the this method in blue here. As it is, the way I actually did it was to go straight for that blue method and then use that to fill in the table, did part B as normal, and then I did it using this green method, but I got a bit confused because I was like, well, actually the multiplier is less. How do we know it's never going to catch up? But it doesn't actually catch up, all because of this number 1250. Anyway, I think that's enough on this question, and it's yeah, it's an interesting one. Just not quite sure about this part here.